And welcome, they'll do the adjustment, to the 34th Leonard A. Ford Lectureship. I'm Dr. Jeff Pribble, and on behalf of the Department of Biochemistry, Chemistry, and Geology, welcome. We are thrilled you are here. So, who is Leonard Ford, and why should we be celebrating his legacy? Dr. Leonard Ford was professor of chemistry at Mankato State College, that's what it was known at that point, from 1939 until his death in 1967. He was chairman of the chemistry department from 1939 to 1947, chairman of the Division of Science and Mathematics from 1947 to 1965, and coordinator of special programs and chemistry professor from 1965 until his death in 1967. Oops, wrong presentation. Sorry, folks. Dan. Dr. Ford earned his undergraduate degree from Gustavus Adolphus College, just up the road, in 1925, and his PhD from the University of Iowa in 1931. Ford made significant contributions to science and education during his tenure at Minnesota State Mankato. He published articles in journals such as Science Education, School Science and Mathematics, and the Journal of Chemical Education. He also published articles with the American Chemical Society and the Minnesota Academy of Sciences. His book, Chemical Magic, was first published in 1959 in hardback and later in 2 editions in paperback. This book achieved international readership, being published in French, Spanish, Danish, and Japanese. Quite a variety of places this work got published. Leonard Ford established the Science Fair at Minnesota State in 1951, and it continues usually being one of the largest science fairs in Minnesota. In fact, I'm a product of that science fair. Back in 3rd and 4th grade, I came and had my science fair project over in the field house area. What is the most common pet? Was my topic. Apparently, I really was trying to convince my parents that we should get a pet. Didn't work. Dr. Ford was instrumental in establishing the nursing program, the medical technology program, dental assisting program, dental hygiene program, and engineering programs at Minnesota State Mankato. Broad range of interests and support for establishing programs for our students. Dr. Ford was recognized by his professional community as a leader. He was president of the Minnesota Academy of Sciences. He served on the Education Committee of the American Chemical Society and was committee chairman, science section of the Minnesota Education Association. He was president of the Mankato Lions Club and served on the board of trustees and alumni boards at Gustavus Adolphus College. This lectureship receives financial support from the Ford family. With us this evening, we are thrilled that one of the daughters of Leonard Ford, Dr. Barbara Olson, and her daughter Kathy G. are with us today. Please join me in welcoming them. We have a couple other distinguished guests with us today. President Inch and his partner Belinda are here. And the provost of the university, Dr. David Hood. Dr. Ford's legacy and all the work he did is worthy of our celebration. So it is my pleasure to introduce our speaker for this evening, Dr. Johna Leddy from the University of Iowa. She's from the chemistry department there. She earned her BA degree from Rice University in Texas and her PhD from the University of Texas. She completed postdoctoral training at Los Alamos Laboratory in New Mexico. She began her academic career at City University of New York, Queens College, and then moved from the city down to Iowa, where she has been rising through the ranks and is now professor. She has 46 high-impact papers. What does that mean? They're recognized by our community as being important for our development and moving our science forward. She holds 33 patents. It says 32 in here. There must have been a new one that since we got this one. And getting patents to be able to help promote science is wonderful for us. She has been president of the, I've lost my place, Electrochemical Society, and has been very involved in that leadership. We are pleased and thrilled to welcome Dr. Johna Leddy as the 34th Leonard A. Ford Lectureship. Dr. Leddy.
Good evening, everyone. We're going to talk about some electrochemistry. So what is electrochemistry? That's the next slide. So electrochemistry is where electricity and chemistry meet. It's at that interface. So the chemistry brings us with conservation of mass. If you put it in the system, it can change form, but it's still in there somewhere. Electricity brings us conservation of charge. So you can't have more cations than anions in the system. So electricity brings us electrons. The chemistry brings us chemical species. Often that's hydrogen ions, protons, and they're there to balance the charge with the electron. You have electrochemistry everywhere. I look at you, and you're a bunch of fuel cells. Okay? All right. So electrochemical generation and storage, it shows up in electrolyzers, fuel cells, batteries, solar cells. It turns up in bioenergy, in photosynthesis, the citric acid cycle. Enzymes are redox catalysts. Vitamins are free radical scavengers. In industry, electrochemistry shows up in aluminum refining, which consumes about 2% of the energy produced in the US. It turns out in fluorination reactions, the Colby reactions, in making certain kinds of polymers. It turns up in the chlor-alkali industry, where we get to make chlorine, sodium hydroxide, and bleach, and other things. And those are important in particularly synthesizing specialized chemicals in just basic chemical processes. I'm going to talk to you a little bit about what I refer to as EERRs. Okay, these are energy and environmentally relevant reactions, and this has to do with generation of CO2 and other greenhouse gases and how we might remediate that or prevent them. I'm going to talk to you about CO2, C1 chemicals, so things between methane and carbon dioxide, one carbon. I'll talk to you a little bit about ammonia and how ammonia generates the third most common greenhouse gas, which is NO2. Hydrogen reactions. There's the hydrogen evolution reaction and the hydrogen reduction reaction. That's the simplest EERR. And I'll talk to you a little bit about oxygen reduction and generation evolution of oxygen. Here we go. So I got a copy of the table of contents and of Chemical Magic, which was written by Professor Ford. And in here is the reactions, and a large number of them are electrochemical. And so here they are: oxygen in the air, the blue flame, burning water, flares, fireworks, I like that one. And then there were assorted other ones. The thermite reaction, iron, magnesium, and aluminum. You get the magnesium hot, it melts the aluminum, and it goes ahead and oxidizes the car engine. Okay, so there's other things, lots of explosions and flares and smokes and so forth. Clock reactions are pretty much all redox reactions. So that iodine clock, that's a redox reaction. Have you ever seen a Zhabotinsky reaction where you've got things changing color and swirling colors all in the same petri dish? Redox reactions. And now we get on to serious things. Okay, so electrochemistry is governed by thermodynamics and it's governed by dynamics. And they tell us different things. They're related, but they're different things. Thermodynamics is when the system is at its minimum energy at equilibrium, and we would characterize that, for example, by a formal potential or a Standard potential. It lets us calculate the maximum energy available in the system, or how much energy we have to put in at a minimum to affect chemical change, electrochemically. Dynamics are the practical side of things. We may be able to design this awesome reaction, and at the same time, there may be practical limitations to what we can actually accomplish. And those practical limitations are dynamics, and they're time dependent. So if we look at kinetics, it's the rates of reactions. And kinetics will eventually evolve down to the thermodynamic state by whatever path it goes by, okay? But it will eventually get back to thermodynamics. We affect kinetics with things like electrodes, electrocatalysts, and catalysts. In electrochemistry, something chemists don't think about too much is transport. How do we get the molecules and reactants from solution to the electrode, and how do we get the product away from that? And so that's another parameter that's part of looking at electrochemical systems. Do we stir? Did we make gases? All those things impact transport. So if we want to design electrochemical systems, we have to balance the best that we can get, the thermodynamics, against the practical limitations that are dynamics. If you wait long enough, you'll get to the equilibrium, but maybe you won't be able to get the battery to give you light up an LED. Okay, so how do we make this work? So we looked at that we have electrochemical reactions between electrons and chemical species. So we typically confine those into a single vessel. And that vessel usually contains an electrolyte with solvent. And the reason is that we want to be able to let the ions move in and out to balance the charge that comes with the electron transfer. Often that involves electrodes, sometimes it involves separators. So we have two classes of reactions. One's a homogeneous reaction where everything takes place in the solution itself. And so it's a one-phase reaction. So this is how, for example, they would use an aldehyde to reduce silver nitrate to put down a silver mirror, an electrodeless deposition. Most of the time, I'll be talking about heterogeneous electron transfers, where I will have at least two phases, electrodes, a solid, and the electrolyte, a solution. You can have more than two, but you have to have at least two for heterogeneous electron transfer. How to think about electrochemistry. You tell people you're an electrochemist and they run out of the room, usually with their hands over their ears. Okay, and it's because of the way electrochemistry is taught. It's an anode, it's a cathode. No, it's a reduction, it's an oxidation. I was a fifth-year graduate student before I could figure out an oxidation for a reduction. That's not the point. We want to chase those electrons around a circuit and figure out where they are and how they are affecting chemical change, okay? So forget everything about the definition of anodes, cathodes, oxidations, reductions, okay? Just chase those electrons. Do not catch them. If you catch electrons, that's bad. Okay, all right. So the way to think about this is in terms of Ohm's law. So voltage is equal to current times resistance. So I have a circuit here. I have a resistor. I have a battery, and the battery is going to have some voltage. I close the circuit, and what happens now is electrons leak out of the negative terminal of the battery, which is the short line. So the electrons come out, they flow through the circuit, it generates a current. And that current is impacted as it flows through the resistor. So I can rearrange Ohm's law, and I end up with I is equal to V over R. Why do I care? Well, V is the energy. How much energy did I put in from the voltage of the battery? Current is the rate. How fast can I affect change in the circuit? And the resistance are the things that impede the flow of current through that resistor. Okay? The resistor is slowing down the rate of the reaction. Pretty much electrochemistry can be thought of this way. Okay? We can have energy input, we can drive a reaction rate or a current, and there are things that are going to slow it up. Okay, so that was one type of reaction. Let's come along now and add an electrochemical cell. All right, so this is my electrochemical cell. This is circle, holds the electrolyte, and I have, in this case, 2 electrodes. And I'm going to drop that into my circuit. Okay, and so now when I close the circuit, the electrons still come out of the negative terminal of the battery. They go through the circuit, and they're going to affect chemical change at the electrode surface, right here. And then we're going to have ions move in between the 2 electrodes, of another chemical change, electrochemical change at the other electrode, and it'll complete the circuit. And so electrochemistry is a circuit. If you close the circuit, you can have electrons move, you can have ions move, and conduction around that circuit is a combination of flow of electrons and flow of ions. Okay, so there's ion conduction and electron conduction, and it all relates back to our Ohm's law. Okay, so let's look at a real reaction. Let's look at water splitting. Okay, so in water splitting, I want to take water and use electrochemistry to convert it back into oxygen and 2 hydrogens. So my reaction's going to go that way. So here are my reactions. I've got a beaker. It's got water and hydrogen ions. It's got some anions in there too. Those are the 2 things we want to look at. Okay, and if I put a sufficient voltage on there, I can decompose this system to make oxygen and hydrogen. I close the circuit. Electrons leak out. On that electrode, the first electrode over here, we're going to convert the hydrogen ions into hydrogen gas, and that'll bubble off that electrode if I'm doing this well. On the other electrode, I'm going to reduce water to make oxygen and some hydrogen ions. Okay? So that's how you would do water electrolysis, split water. So I can look at the thermodynamics for this, and the cell voltage is negative. And that means the free energy is positive. So this is not a spontaneous reaction. Remember, free energy is negative if the reaction is spontaneous. Okay, so it's not spontaneous. We've got some additional issues here. You can build a pretty decent hydrogen electrode. Oxygen's harder. There's about a 400 millivolt potential tax on that. You have to put an extra 400 millivolts past the 1.23 volts. And that's because the oxygen evolution reaction, generation of oxygen, is kinetically slow. You can fix this with really nice catalysts like platinum and platinum group metals, but they're really pricey. So when we look at the circuit, we put energy in with the battery, we ended up generating a rate, a current, and we have things that are slowing it down. So it's slowing it down in part because the kinetics for the oxygen are so poor. This is a water electrolyzer, okay? All right, so we applied a voltage to affect chemical change. If I run this thing backwards, I make a fuel cell. And in that case, I'm going to react oxygen and hydrogen to make water. Okay? You've all seen the demonstration with the balloon with hydrogen and oxygen and the spark. It makes a lot of energy. It's about 0.5 megajoule per mole of oxygen. Okay, so we're going to put my cell in place, and I'm going to put oxygen on one side, oxygen gas, and hydrogen gas on the other. And that will close the circuit. But now what's going to happen is the oxygen is going to react with the hydrogen, and that's going to make water. And so that reaction is spontaneous, and what happens is the electrons come out of the hydrogen electrode, the anode, and they flow through the circuit, and that lets us not power a battery. You could charge the battery, but you can drop that current and voltage, that energy and current, across an electronic device, like your cell phone. And you can use this to charge your cell phone, run a fuel cell, do any number of things. Okay, so that's a fuel cell reaction, and it's spontaneous. And the thermodynamics tell us it's spontaneous because E0 cell is positive, so the free energy is negative, and this thing will spontaneously discharge. We still have some taxes to pay, which have to do with the kinetics for the oxygen electrode mostly. The oxygen reduction reaction is kind of slow, 400 millivolts. We need an electrocatalyst, platinum group metals, which are an expensive hobby, okay? But it goes back to now I'm generating a voltage to drive a current, and I'm overcoming the resistance that includes the oxygen reduction kinetics. Fuel cell, spontaneous release of energy to generate current and voltage to drive an electrochemical process or a reaction. A fuel cell theoretically can be 100% efficient. It has no moving parts, that's part of the reason. And it runs within the temperature range for the solvent. So if I'm in water, I can run between the melting point and the boiling point of water. Okay, so how do we build a fuel cell? So this is a basic fuel cell design, and what we have, here's one platinum catalyst, here's the other platinum catalyst. I feed in hydrogen, it decomposes spontaneously, sends electrons through the external circuit. The hydrogen ions cross this membrane, and that's providing the ion conduction. Oxygen comes in, we've powered the load, electrons, hydrogen ions, and we produce water at the cathode. That's how fuel cells work. In my lab, we add little particles of iron oxide rust, and we can make this device 40% more efficient. So this is something we did in the lab. You can recognize this as a car. It's an electrically powered car. And this is a 10 fuel cell stack. So we've got 10 cells. This is a fan off of an old desktop computer, hydrogen regulator. These are capacitors so we can get enough momentum to get it started. There's the motor. And this is the palladium hydride storage tank to keep the hydrogen stored. It costs more than my car. Okay, all right. So this thing, we built it. It was running around the halls in the chemistry building at 40 miles an hour. Faculty jumping everywhere. It was so fun. Okay, never mind. Okay, all right. So let's talk about how a fuel cell compares to an internal combustion engine, an ICE. First thing to realize that a fuel cell is like a battery because it's an electrical device. We're making electrical energy. But it's like a car in the sense that as long as you feed it hydrogen fuel and oxygen oxidant from the air, it will continue to run. You don't recharge a fuel cell. It's fed fuel, it runs. Here are some of the energy requirements for some different systems. So your average car, if it has an air conditioner, is about 100 kilowatts. Your laptop is less than 100 watts. If you want to power your house, it's 1 to 5 kilowatts. Do you guys know what the biggest energy consumer is in your house? The refrigerator. Okay, and if you want to build a power station, we're talking about multiple megawatts. Okay, so let's compare the fuel cell and the internal combustion engine. Basically, I'm going to try to sell you a fuel cell. All right, so thermodynamically, we can calculate the maximum possible efficiency. If you have moving parts, you lose in this. And combustion engines drive cylinders, there's moving parts, so there's loss. So the maximum efficiency for an internal combustion engine, theoretically, is about 40%. Okay? And a fuel cell is 100%. Now the combustion engine runs at about 300 to 400 degrees Celsius, and the fuel cell runs under 100 degrees. Practically, a well-designed internal combustion engine gets about 30% efficiency. The EPA will tell you the average car in the US runs at 20% efficiency. It's easy to build a fuel cell that runs at 60% efficiency. They've done demonstration projects in a laundromat, and they ran around 97% efficiency, okay? All right. Okay, let's look at the emissions. So carbon dioxide and other emissions while driving. Okay, so this is the EPA. An internal combustion engine gets about 22 miles per gallon and produces 8.9 kilograms of CO2 per gallon of octane gasoline. And so that's a fair amount of CO2. Every one of those carbons produces a CO2, and there's other taxes that are coming out. A fuel cell produces no CO2. And so it produces no NOx gases, and it produces no SOx gases. And it's a little hard to do the comparison, but I can run the fuel cell on 9.6 kilograms of hydrogen per hour if I'm at 60% efficiency. What does that mean? Well, roughly if I had 2.75 kilograms of hydrogen, I could go 22 miles at 77 miles per hour. That's only legal in Texas. Okay. Okay, so the fuel cell is low temperature and the combustion engine is hot, and we're making a lot of CO2, and part of that is keeping the engine hot. So infrastructure, we've been building gasoline cars for a long time. We know how to drill oil, we know how to refine oil, and we know how to drive down the corner to buy gasoline. Infrastructure exists to feed this. If I look at a fuel cell, how am I going to make that hydrogen? I, of course, want to do it by electrolysis, but that's not how we do it. I'll talk about that in a minute. There are no hydrogen filling stations. There's a half dozen of them in California, and they have their own issues. How do we store it? Well, the internal combustion engine, we have a gasoline tank. A fuel cell, how are we going to, dirigible as we drive down the road with the gas? Well, we'll probably pressurize it, or we could store it as a hydride. Hydrides are things like palladium. So the challenges to adopting fuel cell technologies is electrolysis to make the hydrogen. It's viable. You need a good catalyst for the oxygen, preferably earth abundant. Is that how we do it? No. We steam reform methane. We heat up methane and we react it with water to make CO2 and H2. It's a high temperature reaction. And by the time we finish, the amount of energy input and the amount of CO2 generated is roughly the same as if we had burned the octane to begin with, okay? Electrolysis is better, okay. How are we going to store it? Well, hydrogen's got some safety issues, gasoline does not. It's flammable, explosive between 4 and 96%. We could use palladium hydrides because you can put more hydrogen atoms inside palladium than you can by compressing it. Unfortunately, palladium is $30,000 per kilogram right now, so not a good solution. They have special cylinders you can compress things in, and you can run over them with the tank and they won't break, so that's an option. Okay, material cross. So fuel cells run really well, but they're usually got a fair amount of platinum and platinum group metals, and they're expensive. The Nafion membrane has two problems. One is it's very expensive. It's amazing material. It can carry an amp per centimeter squared of ion flux. That's really cool. You could hurt yourself. Okay, you can chew it. It's a superacid, but won't hurt you because the superacids are inside, okay? But it's a fluorocarbon, and that means it puts fluorine into the atmosphere, which is the fourth biggest problem in terms of environmental gases. So we need to do something else there. Okay, so why should we think about and compare the thermal processes and the electrochemical processes? On CO2 generation, thermal processes, because they're used to make heat, have a lot of CO2. And we're combusting a fuel, so they're at pretty high temperatures. Electrochemical produces minimal CO2, depending on what process you're doing, and then there are pretty low temperatures limited by your solvent. Thermal systems have moving parts, pumps and cylinders and so forth, and so that's an inherent loss. There are no moving parts in an electrical device unless you add them. Okay. If we do a reaction, we heat it up, we're just putting heat in indiscriminately. All reactions will get faster. We don't necessarily have much control on the selectivity of the reaction. But if we can control the potential, we can turn a knob on the front of the battery, and we can control how much energy we put in, and we can selectively go ahead and maybe drive one reaction in preference to another. Thermal processes are not really all that portable. They're not very scalable. They're heavy. They're not good for making distributed energy networks. You wouldn't put an internal combustion engine in your laptop, for example. And thermal processes require a lot of peripherals. Electrochemical, they're fairly compact. They don't have a lot of peripherals, and they're fairly scalable. So those are all good things. Are there thermodynamic opportunities to make this thing better? Well, we've been looking at thermal processes for almost 2 centuries now, and there's not a whole lot of room left over to make it much better. We haven't done so much with the electrochemical processes, so there's a big bandwidth where we could improve the efficiencies. Okay, so the infrastructure demands, we know how to do that for thermal processes. We can use electricity for the electrochemical ones, which can come from solar, wind, and nuclear. Okay. The challenges for both of these is if you're looking at energy and environmentally relevant reactions, we need better catalysts, whether we do it thermally or electrochemically. So I hope when you all go home, you'll get on Amazon and buy a fuel cell. All right. Okay, so where does electrochemistry show up? So in industrial electrochemistry consumes 6% of the power, electrical power in the United States. It goes into organic synthesis. So this is the most common organic synthesis, which is to make a diponitrile, the component in nylon, from acrylonitrile. And there's the reaction. So Westchild was at 3M for a long time, and he was very involved with the electrochemical fluoridation of molecules. Here's a scary reaction. They would take glacial HX, no water, pure HF, and they would put 2 huge electrodes in there, and they would dump in alkanes. Then they'd get the fastest, youngest guy in the lab to go in and throw the switch. And they would put in huge voltages and currents and let this thing run, and then turn it off, and then they would separate whatever they made. This is how they did the original electrofluoridations, okay? Glacial HF requires great courage, okay? HF is really bad. All right, so that's how I did the electrofluoridation. We do aluminum refining by melting bauxite, converting it into aluminum oxide, reacting it with carbon, and then we make pure aluminum metal and CO2, and that consumes 1% to 2% of the power in the US. Spent nuclear fuel can be refined electrochemically in molten sodium chloride. You take the spent fuel, that's the anode, you oxidize it, and then you plate uranium at the other electrode. I'll talk a little bit about chloralkali, which is how the chemical industry got started in the US. Oh, I'm sorry, I forgot this slide. This slide is some of the most common electrochemical syntheses that are done commercially. There we go. Now I want to talk to you about chloralkali. Okay, so this is a chloralkali cell diagram, and what we're going to do is take 2 sodium chlorides, 2 waters, we're going to make chlorine gas, hydrogen gas, and sodium hydroxide. So we pump in sodium chloride brine, 26% sodium chloride. We're going to take the chloride and we're going to oxidize it, this is the anode, to make chlorine gas and 2 electrons. And we're going to get a lower concentration of sodium chloride coming out. The electrons are going to be pulled out of here as we're pushing with the battery or the voltage source the electrons into this electrode. We're going to pump in water, we're going to hydrolyze the water, we're going to make hydrogen gas, and we're going to make hydroxide. So we're going to electrolyze the water. The water is going to be pumped out and will consume sodium hydroxide. This too consumes a couple of % of the power. And so once we get the hydrogen out, we can use it to make HCl, ammonia, or we might just burn it for heat. The chlorine comes out. Now this cell has a separator in it, and that keeps the components from mixing. If I do the same reaction with no separator, the hydroxide reacts with the chlorine species, and we end up making hypochlorite, bleach, an oxidizing agent. If we let that sit and go for a while, we'll make chlorate, which apparently is commonly used to bleach wood products to make paper. So that's a chloroalkali cell. Okay. Advanced technologies. So it's not just things that we've been looking at for a long time. Electrochemistry figures in all kinds of advanced technologies. It shows up in transportation, communications, portable electronics, pretty much everything, weird catalysts. You can use it for energy storage and generation, so for batteries, but it also shows up in the phosphors that show up in your screens to make laptops and screens visible. We made great batteries to make better laptops and portable electronics, but that's not only part of the story. Making better phosphors and LEDs were important. How did we arrange and purify semiconductors? How do we put the semiconductors down on the board? How do we drill hole plate things through little holes on the surface? Moore's Law in 1965 said it was going to double the number of circuits on the board every year. We're now down to circuit components in 2024 that are 2 nanometers, 20 angstroms in dimensions. You can put a lot of things on a circuit board. Lithium batteries. I would be remiss if I didn't tell you how a lithium battery works, so this is where this is. Okay, so in a lithium battery, we're going to have we have lithium metal supported on carbon, and when I'm discharging it, I make lithium ions and electrons and leave behind the carbon. On the other electrode, I'm going to bring in the lithium and an electron and plate that on a metal oxide to make, for example, lithium cobalt oxide. So the net reaction is lithium metal on carbon, metal oxide makes carbon with lithium on the metal oxide. So structurally, we have 2 compartments. This is graphite. And graphite's special because the lithium metal ions fit between the sheets of the graphite. Graphite comes in sheets, okay? And then there's a separator. It's a porous separator, and that will let lithium ions move back and forth. And here's the metal oxide. So that's the structure. And this thing makes 3.7 volts, which is really high. So when I'm discharging, the lithium gives up an electron that goes through the external circuit and comes over to the other electron. The lithium ions sit between the graphite sheets, and they go to, the lithium metal sits between graphite sheets, becomes lithium ions. The lithium ions cross the cell, they get over to this side, meet up with the electrons, and deposit lithium on the metal oxide. That's the discharge cycle. If I want to charge it, I put a power source on there, and I force the electrons to go the other way. I make lithium metal, which sits between the sheets of the graphite, and I pull lithium off the metal oxide, and the lithium ions go that way. So that's how your lithium ion battery works. Now, the reason that the batteries catch on fire is they're high energy because of the lithium, and you've all thrown sodium metal into a puddle and seen that glorious reaction. Lithium's even better. Okay, so once it starts to burn, you got a problem. Okay, lithium batteries. So lithium is a critical material, and so the government defines a critical material as a material where the disruption of the supply chain would be a big issue. There's not enough lithium, okay? And it comes from places in the world that might not be so politically stable. Lanthanides are in your magnets, all of your electronics, making all those lovely phosphors. Almost 99% of the lanthanides come out of China. And China has a history of getting mad at a country and stop supply of their lanthanides. Okay, so get ready for gray screens. Okay, so these are critical materials, and electrochemistry can support separation of these materials, recycling of these materials, perhaps extracting lithium, for example, from seawater. Okay, now we're moving into greenhouse gases and the energy and environmentally relevant reactions. So again, the EPA tells us where greenhouse gases come from. So transportation and agriculture, so this would be your burping cows, and this would be just the CO2 that comes out of the cars as we drive along in trucks. Electrical power generation is about a quarter of it. Industry and residential consumption is the remaining component. If we just look at how it's generated, independent of the electrical power, transportation and agriculture are pretty similar, but the bulk of the difference comes out of industry and residential activities. Okay, so carbon dioxide is the biggest problem, comes from heating, burning things. The next one is methane, burping cows, and then nitrous oxide, which comes out of, for example, making ammonia, and the fluorinated compounds are another big deal. Oh, that did that. Okay, so here's a set of EERRs, so energy and environmentally relevant reactions, and you will recognize these as important. CO2 reduction reaction. What can we do to get rid of CO2 we have? Ammonia. Hydrogen evolution and hydrogen oxidation, back to the fuel cells. Oxygen evolution and oxygen reduction, again back to the fuel cells. Methane and C1 chemicals, so methane all the way down through aldehydes and alcohols to the CO and CO2. Those are reactions that are big contributors to environmental gases. Okay, so thermodynamically, these reactions are very low energy. Almost all of them are below 0.6 volts, 600 millivolts. They're small energy reactions. The trouble comes because of the kinetics. They're inner sphere reactions. So I have an electrode, and to make this reaction go, the reactant has to adsorb to the electrode surface. And that's where the problem comes in. That's where the energy tax comes in. That adsorption requires the molecules to rearrange a lot, and that's why it's so energy intensive to get these reactions to go. They're kinetically limited. So here's, this is a reaction that tells me the rate, the log of the rate for the generation of hydrogen, this is HER, as a function of the energy content of the metal. And we end up with these straight lines. And so the rate varies between minus 13, 10 to the minus 13 to 10 to the minus 3, 10 orders of magnitude, and that's only dependent on the metal in the electrode. Okay, so if you want to make a lot of hydrogen, you want a high rate, then you want a platinum group metal. If you want to make no hydrogen, you want something down here. And it turns out these are all tied to the magnetic properties of the metal. But that was this afternoon's lecture, so you're safe. Okay. These are the reaction steps for the C1 chemical. So if I start with carbon dioxide, I could reduce it to CO, or I could reduce it to formic acid. Ants make formic acid. That's why that hurts when they bite. Formic acid can be reduced to the aldehyde. The aldehyde can go to the alcohol, and then we can go to the methane. These are all very low energy reactions thermodynamically, but they all require adsorption to the surface of the catalyst and the right configuration and energy constraints to drive these reactions. It's complicated. Okay, so if I'm going to do something thermally, I just keep heating it until I get there, or pressurizing it. If I'm going to do this electrochemically, I need less heat, I can have some finesse about what reaction I drive because I can control the energy input through the voltage. But we need to understand what's going on fundamentally so we can set up better catalysts, and we want to avoid the Edisonian approach to finding a catalyst. Edisonian means I'm going to go take every metal in the periodic table and see whether or not I can make formic acid rather than CO. If we know what we're doing and understand it better, we can save a lot of time. But we have to think. Thinking is important. Okay, so now we're on to the biological part of this. How am I doing time-wise? Oh, perfect. Okay. I don't have to go to New Jersey. Okay, so redox reactions are central to life. I already told you you're a walking fuel cell, and I want to show you a couple examples of how this might work. This is a potential axis, and this, for example, here's vitamin C. It's here at 0.4 volts, and I can oxidize it to make the oxidized form and open the ring. All of the vitamins fall within about a 3.5 volt range, not very large, less than the lithium battery. And they can be, the red ones are lipid soluble, so they're soluble in the fats, and the blue ones, which are the B vitamins and vitamin C, are water soluble. Okay, so you can overdose on the lipid soluble ones, but the rest of them your kidneys take care of pretty quickly. All right, so they're all electroactive. There's 13 of them. And so they are all free radical scavengers. So if I look, there's a bunch of free radicals down here, but here's a hydroxyl radical. It's a pretty bad actor. If I have a hydroxyl radical, if I bring a vitamin C, for example, the two of them react spontaneously. We know that because on the potential axis, they're on opposite sides. So we'll get a spontaneous reaction. The ascorbic acid dies in the process, but it consumes the free radical, okay? So it's a good free radical scavenger, and all of these are for different reactions, okay? All right, so take your vitamins. Okay, here's two parts of the energy cycles. Photosynthesis is for plants in the light, okay? And they're able to generate ATP, which is the currency for energy in a plant and people. And this is the citric acid or Krebs cycle in kind of a simplified form. So each of these involves multiple steps. So photosynthesis, light comes in, photosystem 2, it makes oxygen and hydrogen, and it also causes a redox reaction with the plastoquinones. And then that reacts with the cytochrome C. We make plastocyanins that feed into photosystem 1. The photon comes in, makes electrons, ferredoxin goes, and we make NADPH, which is a redox mediator. In the meantime, the hydrogens come over here, they cross the membrane through an ATP synthase, and we make ATP for energy, okay? Every one of these steps is less than 60 millivolts, but there's a whole chain of them. And the membrane provides separators that separate charge, and we end up generating a little bit of voltage on each step. And it converts light energy into chemical energy. The Krebs cycle, so we had lunch, and it goes in here, and it goes through this whole cycle. We make NADH, we make some, we use some ATP, and we come up the other side, and so I have it written down because I don't remember. So the Krebs cycle makes 4 carbon dioxides, 6 NADHs, 2 FADHs, and 2 ATPs, okay? So this is how your food energy gets converted into energy as ATP. Very small steps at a time. This is the nitrogen fixation cycle. And so we're going to start with N2, and we're going to send it through the cycle, and it's going to come back. Okay, nitrogen fixation, thermodynamically converting nitrogen to all of these different oxidized species is thermodynamically easy. It's not energetically easy. In fact, it takes 16 ATPs to do this. And all we want to do is to take N2 over here to ammonia, fertilizer. And this is why we like peanuts. Okay, so thermodynamically, it's 100 millivolts for this reaction to get ammonia dissolved. Kinetically, the nitrogen has a triple bond. That's a really hard bond to break. And so all the energy, the 16 ATPs, are going in there to break that bond. Bacteria do this. We've put algae on an electrode, and when you apply a small voltage, it makes 10 times as much ammonia as algae without an electrode. Okay, so, and it's using a metalloenzyme. For example, molybdenum is pretty popular, and because of that metal center, it facilitates this reaction. And so it's a whole series of low potential reactions to make the ammonia. And then the plants absorb the ammonia, or they take the nitrate and convert it in a couple of steps to the ammonium. We make fertilizer by the Haber-Bosch process, which about 30% of the fertilizer. If we don't make fertilizer, good fraction of the population on the earth starve. And it's done by high temperature and pressure, and it's N2, triple bond, plus hydrogen from steam reforming methane to make ammonia gas. It runs at high temperatures, pressures. It consumes 1 to 2% of the global energy on the planet. It generates 3% of the CO2 because of the hydrogen generation, and it uses 3 to 5% of our natural gas. If we could find a better way to do it, maybe pretend we're doing nitrogen fixation like a biological system in small steps at a time, we could reduce or decrease the energy tax and the environmental tax for this. Okay, 2 technology conundrums. And so what we have is, so one of the problems is how do you do CO2 reduction? And do we want to? So should we try to capture or reclaim CO2? I don't know the answer to this question, but there's things to think about. People want to store it underground. You have to transport it, pump it, and pressurize it. It's probably not a good trade in terms of, you're probably going to generate more CO2 than you actually store. There's been suggested to add iron to the oceans in the South Pacific to encourage growth of algae, because the algae will turn the CO2 into less environmental problems, okay? So we could plant more trees. We could protect the rainforest. We need to think about the political consequences globally, and I can't answer that, I'm just a chemist. I personally have confidence in equilibrium, and so during COVID, when no one was driving, the CO2 content of the air dropped 20% in less than 2 weeks. I claim a 4-day work week is the answer, okay? All right, so ammonia fertilizer. We need the fertilizer or people are gonna die. Haber-Bosch is the way we do it. It's probably the best way we can do it thermally. It's a big energy tax. So can we do it from the other direction? Instead of going N2 to ammonia, let's reduce some of the nitrogen oxides. Nitrate. The problem here is how do we concentrate the nitrate and the nitrite as it runs off the fields? Fix that one, okay. We could do algae on electrodes, and so we could look at some of the things that nature does to try to address both of these problems, and maybe that's part of the solution going forward. Okay, so what do we need to do to change the energy distribution? Well, clearly, electrochemistry has some advantages and a few disadvantages compared to thermal processes. We need better catalysts. We need earth-abundant catalysts. You know, $30,000 a kilogram for palladium is fun to play with, but it's not a solution. We need more selective catalysts. We need to think about this in an intelligent way, not just go dump every element in the periodic table into our reaction. We should look at analogs to natural processes. If we can play with the catalyst and do a good job, we can do selective energy input from the catalyst, so we don't make weird byproducts. We can just make what we're trying to make. And with better fundamental understanding, we can suppress Edisonian processes, which give us a lot of data, but they're kind of wasteful. We need research. On the electrochemical side, we've thought about the thermal side for 200 years. Let's think about an alternative to that. Electrochemistry is one option. So questions philosophically in terms of how to deal with the environmental tax and the energy taxes is, what's the tax on the status quo? What are the consequences of continued increase or even maintaining the same amount of CO2? Is that what we want to do? Beyond that, what are our responsibilities and advantages to use the most efficient methods possible? If we can be more efficient, we can take care of a lot of things. How do we promote nascent technologies, advanced technologies that can address some of these questions? And how do we implement whatever we're thinking globally? Okay, so those are some of the questions. One of the most important things is education. People need to understand what the problems are, what the ways to possibly address them, whether some of the thoughts are totally crazy, okay, or whether some of the thoughts could actually make an improvement in our current situation. And that's in large part because even if you have a great research idea, how do you translate that into making it work in the real world? Finally, I would like to thank the Ford family for this excellent opportunity. I would like to acknowledge the folks who've supported the research over the years. These are my graduate students who have graduated. These are the two in the group. These are master's students, postdocs, some of the undergraduates. The blue folks are in the lab now. I'd like to thank you for your attention.
We do have time for a few questions. We do have a mic that we'll ask you to use so that everyone can hear. So questions for Dr. Leddy.
Why do lithium-ion batteries decay or degrade?
So in any battery where you charge and discharge, there's always the possibility of side chemical reactions. So in some batteries, you grow dendrites, and they pierce the membrane, and then the reactants spontaneously discharge, and you're done. Sometimes you just deplete the material. You start with a manganese compound, and over time, it converts into a manganese chloride, and it's got different voltages, and you're done. So each one is a little different, but it's because of the side decay processes.
Question for Dr. Leddy. We've got one up there.
Hey, Dr. Leddy, my name is Will Coghill-Behrens. I'm the new Dean of Global Education here, but just left a 20-year career at the University of Iowa, so go Hawks. Thanks for coming here today. My question, in my role as Dean of Global Ed, we obviously here at MSU, I think, do a decent job, a good job, an excellent job of providing students lab opportunities to learn all of this. But I really appreciate your comment at the end about translating this into the real world, right? As a scientist, as somebody who is, imparting advice on these younger generations, the folks who are going to really help us solve this problem, what advice would you give students in terms of seeking out additional opportunities to enable to bring this sort of thinking and this sort of work to a global sort of audience, global perspective?
So the most important thing is to never abdicate your thinking. Just because some professor stands up here and tells you blah, doesn't mean it's right. Think about it, dissect it, question the assumptions, okay? In terms of different kinds of opportunities, take things that are interesting to you, try to figure out where there are opportunities to go do summer research, look at different graduate programs, maybe in a field a little different than where you started. We make the most progress when people bring a unique set of skills to a problem, and they can bring different insights about how those skills can fit together. Question the assumptions, okay? And never give up, because if you see something, you may be the only one who sees it. Go after it, okay? That's important. And if 100 people do that and 2 people succeed, we can address a lot of these issues. I'm sorry for the other 98% of you, but we need to have that balance, okay? It's never boring. It's always interesting. Go for it.
Another question for Dr. Leddy. Dr. Leddy will be down here up front. If you have a question, you join her down here. Please join me in thanking Dr. Leddy for an informative and a very thought-provoking lecture for us.
Thank you.
And a couple last things. Please accept a token of us, a copy of Chemical Magic by Leonard Ford, revised in 1993 by Wynne Grunmeyer, who was a faculty member here and one of Ford's students. And then also your very own chemical test tube
Oh,
pen.
thank you. I've been envying yours. Excellent.
The lectureship like this doesn't just happen. There are many people who work on this. Chris Cords, who will not want to be recognized, is sitting over here, does a lot of the behind-the-scenes work. So please join me in thanking Chris for all the work she does. My colleagues in the Department of Biochemistry, Chemistry, and Geology helped by promoting this. I really want to thank Dan Swart for all the work he did today, and Dr. Trent Vorlichuk for the work he did with that. Our student clubs, the Biochemistry Club and the Chemistry Club, both helped with various aspects today. They had lunch with Dr. Leddy, asked her wonderful questions. They helped with a variety of things, so I want to thank them. We look forward to seeing each of you next year for the 35th Leonard A. Ford Lectureship. Stay tuned, not sure what day, what the topic will be, or the speaker, but going to be a tough act to follow. So there are cookies and punch out this way. Stop and say hi to Dr. Leddy, ask a question, and safe travels, and have a great evening. Thank you.